All right, in part two, we are going to be looking at systems of nonlinear equations now in two variables. And then in this video, we will also be looking at graphing inequality systems of equations. So when we talk about nonlinear equations, we're talking about things like parabolas, circles, cubic functions, square root functions, any other type of function we could look at. And solving these algebraically takes a little bit more problem solving than what we were looking at before. So in this case, we still have using substitution and elimination as options, but we might get more than just one solution. It's not just those three possibilities anymore of one solution, no solutions, or infinitely many. It is possible that we could get infinitely many. It's also possible we could get no solutions, but it's possible we could get 1, 2, 3, 4, 5 solutions. There's so many different possibilities. Let me just kind of show you graphically what I mean by so many different possibilities. Let's just take a parabola and a straight line. If I have a parabola and a straight line, it's possible that they intersect at 2 points. A parabola and a straight line, possible that they don't intersect at all. A parabola and a straight line, possible that they intersect at 1 point. Let's take a circle and a parabola. If I have a circle and a parabola, it's possible that they intersect at 2 points. It's possible that they intersect at 4 points. Possible that they intersect at 3 points. It's possible that they intersect at 1 point. It's possible that they don't intersect at all. Just with a parabola and a circle, so many different possibilities here. What if we have two parabolas? It's possible that they don't intersect at all. It's possible that they intersect at 2 points. It's also possible that they intersect at 1 point where their vertices, their vertex is at the same place. So again, so many different possibilities. So when we solve these algebraically using the addition and substitution methods, you really want to try and get down to only having one variable. So when I'm looking at these equations here, I'm thinking, how can I get rid of either all of my x's or all of my y's? And the easiest way to do that here would be to use substitution. I can solve this equation for y, so I could get y by itself and plug that in here so that this top equation just has x's. Now, getting y by itself here, I could add y to the other side and subtract 9 over, and that would give me 3x minus 9 equals y. So substituting that in for y here, then I have x squared equals 2 times y plus 10. Y is equal to 3x minus 9. X squared equals, distributing that to 6x minus 18 plus 10. And this is a quadratic equation, so I want to get all of my variables on one side. So, or get all of my terms on one side and set it equal to 0. So x squared and subtracting 6 over would be minus 6x. Negative 18 plus 10 is negative 8, so if I add 8 over equals 0. I can use the x method, and factoring this, that'll be x minus 4 and x minus 2 equals 0. So x is equal to 4 and x is equal to 2. Now remember, we're talking about points where these equations intersect. So when I'm talking about points, I always want to answer with coordinates. So I'm going to have an x value of 2 and find the matching y value, and an x value of 4 and find the matching y value. Well, I have an equation with y. So y is equal to 3x minus 9. I can go ahead and plug in 3 times 2 minus 9. Well, that's 6 minus 9. That gives me negative 3 when x equals 2. And when x equals 4, so plugging in 4, 3 times 4 is 12, minus 9 is positive 3. So those are my solutions. Next example here, we have y, or x minus y equals 3, and then we have the equation of a circle. X minus 2 squared plus y plus 3 squared equals 4. That's the equation of a circle. I'm going to go ahead and solve for one of my variables here. The easiest one to solve for would be x. If I add y to the other side, x is equal to y plus 3. And I'm going to go ahead and take that and substitute that in for x. So x is y plus 3 minus 2 squared plus y plus 3 squared equals 4. Well, that becomes y plus 1 squared plus y plus 3 squared equals 4. I'm going to go ahead and FOIL both of these out. If I use the box method on each of these, this one becomes y squared plus 2y plus 1. This one becomes y squared plus 6y plus 9. And these are quadratic this is a quadratic equation. I want to combine like terms and get it set equal to 0. So 2y squared, 2y and 6y is 8y. Excuse me. 1 plus 9 is 10, equals 4. Subtracting 4 over, that's 2y squared plus 8y plus 6 equals 0. And all of those numbers are divisible by 2, so I can divide both sides of my equation by 2. That becomes y squared plus 4y plus 3 equals 0. Using the x method, I can factor that, and factoring that gives me y plus 3 and y plus 1. So what we have here then is y equals negative 3 and y equals negative 1. So plugging those in, we can find the matching x coordinates. What we have here are the y coordinates. So I have y equals negative 3 and y equals negative 1. So I can find the matching x values. Now we know x is equal to x equals y plus 3. So y is negative 3 plus 3 would be 0. And negative 1 plus 3 equals 2. And those are my 2 points where these intersect. Let's do a couple more. Here we have a circle and an ellipse. And we're going to go ahead and the last two we've used substitution, but this is a good setup for using elimination. I'm going to multiply the bottom equation by negative 1. And then the top equation will stay the same, so 4x squared plus y squared equals 13. The bottom equation will become negative x squared minus y squared equals negative 10. The y's or y squareds cancel out, and I have 3x squared equals 3. Dividing both sides by 3, x squared equals 1. Square rooting both sides, x equals plus or minus the square root of 1, which is 1. So from here, I have an x coordinate of 1 and an x coordinate of negative 1. So I can use either one of those equations to solve for y. I'm going to use the bottom equation, so I'm going to use x squared plus y squared equals 10. And plugging in positive 1 for x, well, 1 squared is 1 plus y squared equals 10. Subtracting from 1 from both sides, y squared equals 9, so y equals plus or minus 3. So for that one x value of positive 1, I got two y values, 3 and negative 3. So that means for that one x value, there were two y values that matched with it. So plugging in negative 1, the same thing's going to happen. Negative 1 squared is 1. And subtracting 1, we get y squared equals 9. Then plus or minus 3. So for negative 1, we also got 3 and negative 3. So for these equations, there are 4 points where they intersect. For the next one, it is again a good setup for substitution, but it is also possible to use the addition method. So this is a good example for me to show you both methods with the same example so you can see that you can do it either way. So I'm first going to use substitution. And then I'll do it again using elimination or the addition method. So using substitution, I'm going to go ahead and substitute that in for y. So x squared plus y squared equals 9. And I'm plugging in x squared plus 3. And when I square that using the box method, I have x squared plus x to the 4th power plus 6x squared plus 9 equals 9. And then subtracting 9 from both sides, I have x, or actually, let me combine like terms here. I have x to the 4th power. X squared plus 6x squared is 7x squared. We subtracted 9 from both sides, so that's equal to 0. I can factor out an x squared, and then I have x squared plus 7 equals 0. And x squared equals 0 means x equals 0. And then x squared plus 7 equals 0, subtracting 7, square rooting both sides, I have x equals plus or minus the square root of 7 with an I on it because it has a negative inside. And if you're going to get imaginary numbers, that does not actually give me a point where they intersect. So that doesn't give us any solutions or any real solutions. So the only x value I really got here was 0. So plugging that in for my x value, I can find y by plugging in 0 here. 0 squared is 0 plus 3 is 3. So that's the only point where these two equations intersect. Now let's see what happens when we do this with the addition method. So if I'm using the addition method, then I want to get the x squared on the other side so that I can add those together. So subtracting that over, that would be negative x squared plus y equals 3. And then I'd have x squared plus y squared equals 9. Adding those together, the x squareds cancel. Y squared plus y are not like terms, so I'd have y squared plus y equals 3 plus 9 is 12. This is a quadratic equation, so I want to get it set equal to 0, so y squared plus y minus 12 equals 0. I can factor that using the x method, and that would be x plus 4 and, oops, not x, y, we're talking about y's here. Y plus 4 and y minus 3 equals 0. So y equals negative 4 and y equals 3. Well, from here we can go ahead and plug in to find our matching x values. So negative 4 and 3. And I can plug it into either one. I'm going to go ahead and plug into what was the top equation. So this was y equals, actually, since we used that one with the other one, let's use the bottom one. I'll use x squared plus y squared equals 9. So we don't know x squared plus y squared. So negative 4 squared is 16 equals 9. Subtracting 16 from both sides, I get x squared equals 7, or negative 7. And the same thing happens. I would have those i's. So that means that can't give me a solution since that would be imaginary. Let's do the same thing. So x squared plus y squared, which is 3. So 9 equals 9. Subtracting 9 from both sides, x squared equals 0. So x equals 0. So we got the same solution two different ways. You could do it either way, and they get you the same answer. All right, we're going to switch from systems of equations that are nonlinear in two variables to now looking at systems of inequalities. Again, could be linear, could be nonlinear. A couple things we need to recall about systems or about inequalities in general. One, if you divide both sides of an inequality by a negative, you need to flip the direction of the inequality. When you're working with inequalities, if you have the ones that don't have the equal to sign, you'll have a dashed line. And if you have the line with the equal to sign underneath, you'll use a solid line in graphing. All right, so this first example here, we have x minus y is less than 1. You could solve for y and use slope-intercept form to graph these, or what you could do is use the intercepts. So you could plug in 0 for x. If I plug in 0 for x, solving for y, y equals -1. If I plug in 0 for y, that term goes away, and x equals +1. So I could use those 2 points to graph. So 0, -1, and 1, 0. And I could continue plotting more points with that slope. And then because it doesn't have the equal to sign, this is going to be a dashed line. So I can go ahead and draw that dashed line. And then I need to determine if I'm shading above or below the line. Well, the way we determine that is by plugging in a test point. And the easiest point for us to use is the point 0, 0. As long as that is not on the line, you can use it. 0, 0 is not on this line, so I can use that. Plugging in 0 for x and 0 for y, 0 minus 0 is 0. 0 is less than 1. So if when you get that test point, you get something that's true, like that, 0 is less than 1, then you shade on the side of the test point. If I got something that was false, so let's say it was facing the other way, 0 is greater than 1, then I would shade on the opposite side of the test point. Okay. This one you can also use intercepts. If I plug in 0 for x, that term goes away, dividing by 3, y equals 4. And if I plug in 0 for y, that term goes away, dividing by 2, x equals 6. So I can plot those points, 0, 4, 1, 2, 3, 4, and 6, 0. So those 2 points. And this is a solid line because it has the equal to line here. So I can go ahead and draw that line. I need a test point. Again, I'm going to use 0, 0 since it's not on the line. Plugging in 0 for x and 0 for y, 0, 0. 0 is greater than 12. Well, that's not true. 0 is not greater than 12. So I'll shade on the opposite side of the test point. So when you're answering these questions, your answer is where the shading area is overlapping. That's my answer. It's that green shaded area. All right, so those were both linear equations. What if we have something that's not linear? So this next one, we have one linear equation, and then we have a circle. So the top equation is a linear equation. My y-intercept is -1. My slope is +2/5, so up 2 and over 5 in a positive direction, or I could go down 2 and over 5 in a negative direction. It does not have a line underneath, so that means it's going to be dashed. And I can use a test point. 0, 0 is not on the line, so I can use that. 0 for x, 0 for y, 0 is greater than -1. Well, that's true. 0 is greater than -1, so I'll shade on the side that the test point was. This is a circle with a center at the origin and a radius of 3, so I can go out 3 in each direction. And then it's a solid line because it has the line underneath. And now we either are shading inside the circle or outside the circle. And the way we can determine that is by the test point. So I can use 0, 0 again since it's not on the circle. 0, 0, 0 is less than 9. Yes, that's true. So we're shading inside the circle. And the overlapping part would be this space here. I like using highlighter to do the shading just because it makes it clear what the overlapping area is. We're going to do just a couple more. And here, now we have 3 equations. So you can have more than just 2 equations. You could have 3 or 4 or however many. The first one is a parabola. It's a parabola that's going down since our a value is negative, and it's been shifted up 4. So you can see how as we progress through more material, it's testing all your prior knowledge, making sure you still know how to graph parabolas and all of that. So it's a solid line, so I can go ahead and draw that solid line there. And test point, it's either going to be inside the parabola or outside the parabola. So 0, 0, 0, and 0, 0 is less than 4. Yep, that's true. So I'm shading inside that parabola. And then this equation here, I can use those test or the Intercepts again. 0 for x, dividing by negative, that would be 2. And then 0 for y, that would be negative 2. So 0, 2, and negative 2, 0. So solid line. 0, 0 is not on that line, so I can use that as a test point again. 0 and 0, 0 is greater than negative 2. That's true, so I'm shading below that line. And then the last one, y is greater than negative 5. So 1, 2, 3, 4, 5, dashed line. And it's saying greater. Well, that would be above the line. If it was less than, it would be below the line. So I'm shading above that line. So my overlapping area is where all three of them overlap, and that would be this space here. Okay. Couple more. Here we have 2x plus y is less than or equal to negative 2, and then both, again, linear equations here. So the top one, I can go ahead and subtract 2x so it's in slope-intercept form. So y is less than or equal to negative 2x minus 2. Y-intercept of negative 2, slope of negative 2, so up 2 and over 2 in a negative direction, or down 2 and over 2 again in a negative direction. Solid line. And test point, if I plug in 0, 0, 0 and 0, 0 is less than negative 2. Yes, or no, it's not. It's greater than negative 2. So I would shade on the opposite side. All right. And then this bottom one, you could use intercepts or you could solve for y. It's really up to you. I'm going to go ahead and solve for y. So solving for y, subtracting 6x over, I have 3y is greater than negative 6x plus 6. And dividing by 3, y is greater than negative 2x plus 2. So now I have a y-intercept of positive 2 and a slope of negative 2. Notice those are the same slope. That means these lines are parallel. And this would be a dashed line here because there's no equal to sign. And again, it does not go through 0, 0, so I can use that as my test point again. 0 and 0, 0 is greater than 6. Well, that's not true. So we're shading on the opposite side from the test point. And notice here that there is no overlapping area. That means there's no solution because there's no overlapping area. So I would want you to actually write that, no solution, and I'd want to see these two areas shaded with no overlapping area. One more example here. And here we have a vertical line and a horizontal line. Horizontal line, y equals negative 1, and dashed line there. And it's saying y is less than negative 1. Well, that would be below that then. And then here we have 2x is greater than negative 6. If I divide by 2, I have x is greater than or equal to negative 3. So vertical line at negative 3, and it'll be solid, so it has the equal to sign. And x is bigger than that, so that would be the values to the right. So the overlapping area then, would be all of this. And that is the end of part 2.